Hello, friend. Welcome back to another quiet journey through the cosmos. I'm so glad you're here. Some nights the sky feels impossibly vast. You step outside, tilt your head back, and suddenly you're small again. Childlike. The darkness above isn't empty, it's breathing with light. Tiny pinpricks scattered across black velvet, each one a sun burning millions of miles away. And somewhere in that ancient human corner of your mind, a question rises. The same question our ancestors whispered 5,000 years ago. How many, how many stars are there? Can they even be counted? Tonight we're going to follow that question through time. From ancient priests squinting at the heavens to modern satellites mapping 1 billion stars in a single sweep. It's a story about curiosity, humility, and the stubborn human need to measure the immeasurable. And maybe it'll help you drift into sleep, knowing something beautiful about this universe we share. Before we begin our drift through the cosmos, if you find peace in these quiet explorations, you might like to stay a while. Go ahead and gently tap the like button. It helps others find this corner of calm. And if you'd like more science told softly, consider subscribing and ringing the little bell, not for noise, but so the next quiet night can find you again. Now, let's begin. Picture this. It's 3,000 years before satellites, before telescopes, before electric light drowned the Milky Way. You're standing in a desert, Babylon perhaps, or the plains of ancient China. The air is cool, dry, perfect. Above you, the sky doesn't just glow, it roars silently with stars. Thousands of them, tens of thousands maybe. The Milky Way cuts across the darkness like spilled milk, exactly as the Greeks would later name it. You can see star clusters, nebulae, the faint smudge of Andromeda. Though you don't know, that's a galaxy yet. You think it's just another cloud of light. Everything up there feels close enough to touch, but impossibly far at the same time, and you wonder, you can't help it. How many? This question, simple, innocent, profound, might be the oldest scientific question humanity ever asked. Long before we understood gravity evolution or atoms, we wanted to count the stars. Not just see them, not just worship them, count them, name them, own them in a way. It's such a human impulse, isn't it? To quantify the infinite, to take something overwhelming and break it into numbers we can hold. The earliest astronomers didn't have much to work with. No computers, no cameras, just eyes, patience, and an unshakable belief that the cosmos followed patterns. In ancient Babylon, around 1200 BCE, priests recorded the movements of planets and the positions of bright stars on clay tablets. They didn't count all the stars, that would have been madness, but they noted the important ones: Venus, Jupiter, the brightest stars and constellations they used to track seasons and predict eclipses. These were practical people. Farmers needed to know when to plant. Kings needed omens before battles. The stars weren't just beautiful, they were useful. In China, astronomers went further. By 300 BCE, they had catalogs listing over 1,000 stars organized by position and brightness. They divided the sky into sections like a celestial map. Some stars were emperors. Others were ministers or generals. The sky mirrored the empire below. It's fascinating, isn't it? How we project ourselves onto everything, even the heavens. We see order because we crave it. We see hierarchy because we live in it. But here's the thing. None of these ancient astronomers thought they were counting all the stars. They knew deeply intuitively that what they saw was just a fraction, a glimpse. The universe was keeping secrets, and humans, stubborn as we are, decided we'd uncover them, one star at a time. The Greeks took this obsession and formalized it. Around 300 BCE, a mathematician named Eudoxus tried to describe the motion of stars and planets using nested spheres. Imagine the universe as a series of transparent crystal shells, each one rotating at different speeds, carrying the sun, moon, planets, and stars. It was elegant. Wrong, but elegant. And it did something important. It turned the sky into a problem that could be solved, a puzzle with rules. If you studied hard enough, you could predict where Mars would be next month, where the sun would rise on the summer solstice. Knowledge became power. Magic became math. Then came Hipparchus. We'll talk more about him soon, but for now, just know this. Around 190 BCE, on the island of Rhodes, a man looked up and decided to do something extraordinary. He would catalog the stars, not just the brightest ones, not just the ones priests cared about, all of them, or at least as many as his eyes could see. He spent years, decades perhaps, staring at the sky night after night, writing down positions, noting brightness levels. When he was done, his catalog listed over 1,000 stars. Each one measured, each one mapped. It was humanity's first true attempt to count the cosmos. And it was hopelessly incomplete. But he didn't know that yet. None of them did. Imagine his wonder, though. Imagine thinking you've cataloged the universe, that you've done it. You've counted the stars, or at least the ones that matter. There's a kind of beautiful arrogance in that. A confidence we've lost in the modern age now that we know the Milky Way alone holds hundreds of billions of stars, most of which we'll never see, never name, never count. Hipparchus thought he'd finished the task. He was off by a factor of 100 billion, and yet his work mattered. It was the foundation, the first brick in a wall that would take 2,000 years to build. Because here's the truth. Counting the stars isn't really about the number. It never was. It's about the journey, the methods we invent, the tools we build, the errors we make and correct. Every time we improve our count, we learn something new about the universe and about ourselves. We learn that we're smaller than we thought, that the cosmos is stranger, older, bigger than our ancestors could have dreamed. And somehow, that doesn't make us feel insignificant. It makes us feel connected, part of something vast and ancient and ongoing. Do you ever think about that? How every question leads to 10 more questions. How every answer is just a door opening onto deeper mysteries. The ancient astronomers thought the stars were fixed points on a celestial sphere, eternal, unchanging. They didn't know stars are born in clouds of gas, that they live, burn, and die, that our sun is just one of 400 billion siblings in this galaxy alone. They didn't know galaxies existed. They thought the Milky Way was mist, a smudge, a mystery they'd solve someday with better eyes. And in a way they were right. Better eyes did come. Glass lenses, mirrors, silicon detectors, satellites. Each generation built better tools and saw further. But the question remained, how many stars? And with every new answer, the universe seemed to whisper back, more than you think, always more. On those ancient nights under skies unpolluted by city glow, our ancestors saw roughly 6,000 stars with the naked eye. That's it. 6,000 if conditions were perfect. If you were in the desert far from dust and moisture, if your eyes were sharp and young, most people saw fewer, maybe 3,000 on a good night. And yet, those 3,000 to 6,000 stars felt like infinity. They named them, told stories about them. Orion the hunter, Cassiopeia the queen, Ursa Major the great bear. Each constellation a story, a memory, a way of organizing the chaos above. But even then some suspected, some wondered, what if there are more? What if the faint glow between the bright stars isn't emptiness, but distant lights, too dim to see clearly? What if the universe is hiding most of itself from us, waiting for us to invent the right tool? Ask the right question, look the right way. They were right, of course. The universe was hiding, not out of malice, not as a test, just because that's what distance does. It softens light, stretches it, scatters it. By the time starlight reaches us, it's been traveling for years, centuries, millennia. Some of the stars you see tonight died before you were born. Their light is a ghost, a postcard from the past, and counting those ghosts. That's the task we've been attempting for 3,000 years. So tonight, as you settle in, as your breathing slows and your mind begins to wander, remember this. You're part of that ancient lineage, the stargazers, the counters, the dreamers who looked up and refused to accept infinity as an answer. You're lying here under the same sky. Hipparchus studied the same stars, shepherds watched over their flocks. The cosmos hasn't changed much, but our understanding has. And it's still growing, still reaching, still counting. One star at a time. And maybe that's enough. To be part of the count, part of the search, part of the quiet, endless wondering. Let that thought settle softly. There's no rush, we have all night. And the stars. They'll wait. They've been waiting for billions of years. They can wait a little longer. But to understand how we move from counting 6,000 stars to mapping billions, we need to meet someone. A man with sharp eyes, sharper math, and a gift for seeing patterns in chaos. His name echoes through astronomy, even now 2,000 years later. Hipparchus of Nicaea, born around 190 BCE on the coast of what we now call Turkey. Died around 120 BCE, probably on the island of Rhodes. 70 years of life, most of it spent staring upward. He wasn't the first astronomer, not even close. But he was the first to treat the night sky like a problem that demanded precision. Not poetry, not mythology, numbers, coordinates. Measurements accurate enough that sailors could navigate by them, that future astronomers could verify them, that 2,000 years later, we'd still be talking about his work. Imagine standing where he stood, the island of Rhodes jutting into the Aegean Sea. Warm Mediterranean nights, air so clear you can see the curve of the Milky Way, like a river of light overhead. No cities to wash out the stars, no street lamps, no skyscrapers, no airplanes blinking red across the dark. Just you, a writing tablet, and approximately 6,000 visible stars scattered across the dome of heaven. Your task, write them all down. Every single one. Note their positions. Measure their brightness. Create a map so precise that anyone, anywhere could use it to find their way. That was Hipparchus's gift to humanity. The first true star catalog. Somewhere between 850 and 1,080 stars, depending on which ancient sources you trust. Each one carefully observed year after year. He didn't just list them randomly. He organized them by constellation Orion, Taurus, Leo. All the familiar shapes his culture had named generations before. And then brilliantly, he did something no one had done systematically before. He ranked them by brightness. He created what we now call the magnitude system. First magnitude stars were the brightest. Sixth magnitude were the faintest his eyes could detect. It seems so simple now, doesn't it? But think about what that required. Consistency. A trained eye that could judge night after night, whether this star or that star glowed more intensely. No instruments, no photometers. Just the human eye, that imperfect detector, trying to measure light across vast distances. Scientists suggest that Hipparchus could distinguish differences in brightness of about half a magnitude, roughly a 60% change in light intensity. That's impressive for naked eye observation, but it also meant his system was subjective. Two observers might disagree. One person's second magnitude star might be another's third. And here's the beautiful mistake, the one that would echo through astronomy for 2,000 years. Hipparchus assumed all stars were basically the same distance from Earth. They sat on a celestial sphere. He thought a great cosmic shell surrounding our planet. Some stars were brighter, simply because they were inherently more luminous, like bigger torches. He couldn't have known that stars vary wildly in distance. That Sirius looks bright, partly because it's close only 6 light years away, while Rigel in Orion blazes, despite being 860 light years distant, because it's a blue supergiant tens of thousands of times more luminous than our sun. This error didn't make his work useless. Far from it. His catalog became the foundation of Western astronomy. Ptolemy, writing 3 centuries later, incorporated Hipparchus's observations into the Almagest, the astronomical textbook that would dominate European and Islamic science for over 1,000 years. But the assumption of equal distance created blind spots. It made it harder to understand the true nature of stars. It reinforced the idea that we sat at the center of a small, comprehensible universe. A comfortable thought, a wrong one. What did Hipparchus actually see when he looked up? Let's walk through it. On a perfect night under ideal conditions, the human eye can detect stars down to about magnitude 6.5. That gives you roughly 6,000 stars total, though only half are visible at any given time, because the other half are below the horizon. So, on any single night, Hipparchus could observe maybe 3,000 stars. To catalog them all, he needed years, watching as constellations rose and set with the seasons. Orion dominating winter skies, Scorpius crawling across summer nights. He had to compensate for the moon's brightness for atmospheric haze for his own fatigue. Some nights the seeing was perfect. Other nights, moisture in the air dimmed everything. Research shows that atmospheric conditions can change a star's apparent brightness by up to half a magnitude. On humid nights, sixth magnitude stars might vanish entirely. On crystal clear desert nights, you might glimpse stars as faint as magnitude 7. Hipparchus didn't have control over these variables. He did his best. He developed methods to minimize error observing the same stars, repeatedly comparing them to reference stars, checking his work across seasons. It was meticulous, obsessive even, the kind of work that requires a special temperament, patience, faith that the effort matters. And it did matter, because hidden in Hipparchus's catalog was a discovery that would shake the ancient world's confidence in eternal, unchanging heavens. Around 134 BCE, he noticed something strange. A bright star had appeared in the constellation Scorpius. Just appeared. One night it wasn't there, and then it was shining brilliantly among the familiar stars. We'd call it a nova today, probably a white dwarf star that had pulled material from a companion, heated up, and exploded in a temporary burst of fusion. But Hipparchus didn't have that explanation. He just had the observation. A new star, in a cosmos that was supposed to be perfect and unchanging since creation. This discovery rattled him enough that he decided to create his catalog. If stars could appear, maybe they could also disappear. Maybe the heavens weren't as stable as philosophers claimed. Maybe future astronomers would need a record of what the sky looked like in his era so they could detect changes. It's fascinating how one anomaly can redirect an entire life's work, isn't it? How a single unexpected star can birth a catalog that lasts millennia. Hipparchus couldn't have known that his meticulous list would still be referenced 2,000 years later, that his magnitude system, refined and made logarithmic in the 19th century, would remain the standard way astronomers describe stellar brightness. But let's talk about what he missed, because the limitations are just as instructive as the achievements. Hipparchus cataloged roughly 1,000 stars. Sounds impressive until you realize the Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. He saw 0.0000001% of them. Not even a rounding error, a whisper of a fraction. And it's not like he was lazy or unambitious. He was working at the absolute limit of human perception. The problem was biology. The human eye, for all its elegance, is a terrible telescope. Here's why. The pupil dilates to about 7 millimeters in darkness. That's your aperture, your light gathering ability. Compare that to even a small modern telescope with a 4-inch aperture about 100 millimeters. That telescope gathers over 200 times more light than your eye. It can see stars down to magnitude 12 or 13, revealing thousands of stars in a single constellation where Hipparchus saw dozens. And that's just a backyard telescope. Professional observatories use mirrors meters across. Space telescopes avoid atmospheric distortion entirely. They see billions of stars, whole galaxies hidden in what Hipparchus thought was empty darkness. There's another limitation too, one Hipparchus couldn't have anticipated. Light pollution. In his era, the darkest nights were truly dark. The brightest artificial light was a torch or an oil lamp, nothing that could compete with starlight. Today, 80% of humanity lives under light-polluted skies. In major cities, you might see only a few dozen stars on a clear night. The Milky Way, that great glowing river Hipparchus knew intimately is invisible to two-thirds of people in the United States and Europe. We've traded dark skies for electric light, and in the process, we've lost access to the universe. We've made ourselves strangers to the night. Hipparchus also worked alone. No collaborators as far as we know. No team of assistants cross-checking his observations. Just one man, one set of eyes, one perspective. Modern astronomy is a collective endeavor. Thousands of scientists analyzing data from telescopes scattered across the globe and in orbit. They share findings, instantly correct each other's errors, build on each other's work. Hipparchus had none of that. He had his notes, his solitude, and the quiet conviction that what he was doing mattered, that future generations would need this knowledge. He was right. One of the most remarkable things about Hipparchus's work was his understanding of precession. He compared his own observations with star catalogs made a century and a half earlier by Babylonian astronomers and noticed something odd. The positions of stars relative to the equinoxes had shifted, not much, about 1 degree per century. But it was real, measurable. He correctly deduced that Earth's axis wobbles slowly over time, like a spinning top winding down. It takes about 26,000 years to complete one full wobble. This meant the fixed stars weren't quite as fixed as everyone thought. The celestial coordinate system itself was drifting. Without Hipparchus's careful measurements, this discovery might have waited centuries. Think about the humility required to notice that. To realize that even your reference frame is moving, that nothing in the universe is truly still. Everything is shifting, rotating, orbiting, drifting through space. We're all in motion all the time, even when we feel perfectly stationary. Hipparchus glimpsed that truth not through grand theory, but through patient observation. Small discrepancies adding up over time. It's a lesson in attention, in trusting your data even when it suggests something uncomfortable or strange. Now, was Hipparchus's catalog perfect? Of course not. He made errors. Some positions were off by a degree or more. Some stars were misidentified. Some bright variables like Algol probably confused him. Algol dims and brightens every 2. 87 days is an eclipsing binary system, but Hipparchus might have thought its varying brightness was measurement error. He listed some stars that don't seem to exist possibly because he saw planets or comets and mistook them for fixed stars. He also missed the faint nebulous patches, what we now know as galaxies and star clusters, because they were too dim and diffuse for his eye to resolve. But mistakes don't diminish the achievement, they humanize it. Hipparchus wasn't a god with perfect knowledge. He was a person with clever methods and dogged persistence doing the best he could with the tools available. Every scientist who came after him, Ptolemy, Al-Sufi, Tycho Brahe, all the way to modern astronomers, stood on his shoulders. They refined his methods, corrected his errors, expanded his catalog. But they were building on his foundation, that first act of systematic observation, that first insistence that the sky could be mapped, measured, understood. So, what's the lesson here? Maybe it's this. Precision matters, but so does acceptance of imperfection. Hipparchus knew his eyes had limits. He knew atmospheric conditions varied. He knew he might be making mistakes, but he did the work anyway. He didn't wait for perfect tools. He used what he had. And in doing so, he changed how humanity thought about the stars. He turned them from gods and myths into data points. Objects that could be studied, predicted, understood. Not to drain the mystery from them, but to deepen it. To ask better questions. Do you ever feel that way? Like you're working with imperfect tools, limited information, trying to make sense of something vast and complex. Maybe that's the human condition. We're all a bit like Hipparchus, squinting at immensity, trying to count what cannot be fully counted, measure what exceeds measurement. And yet we try. We make our catalogs, our lists, our maps. We impose order on chaos, knowing full well the order is temporary, incomplete, subject to revision. But it's enough. It has to be. Because the alternative is to look at the sky and feel only overwhelm. And where's the peace in that Hipparchus gave us permission to approach the infinite one star at a time, to break the overwhelming into manageable pieces, first magnitude, second magnitude, third. This constellation, then that one, year after year, a lifetime spent looking up. And when he died, the sky was a little less mysterious. Not because he'd solved it, the universe doesn't get solved, but because he'd shown it could be studied. That patience and method could yield knowledge. That one person armed with nothing but eyes and determination could add something meaningful to the human understanding of existence. That catalog of 1,000 stars was just the beginning. But every journey starts with a first step. Every count begins with one. And Hipparchus, standing on that rocky island 2,000 years ago, counting stars by their brightness, gave humanity its first real glimpse of the task ahead. A task we're still pursuing, still refining, still lost in beautifully. But even as Hipparchus's work was being copied and preserved, passed from Greek to Arabic to Latin, scattered across libraries and monasteries, something was about to change. A new tool was coming, one that would shatter everything the ancients thought they knew about the number of stars. Venice, 1609. A glassmaker's workshop smells of sand and fire. Someone has figured out how to grind lenses in a particular way. One convex, one concave, and mount them in a tube, pointed at a distant church steeple, and suddenly the cross on top looks close enough to touch. It's a novelty. A merchant's tool may be useful for spotting ships on the horizon. No one is thinking about stars, no one except a mathematics professor in Padua with restless hands and a habit of questioning everything. His name is Galileo Galilei, and he's about to multiply the universe. That winter, Galileo took the spyglass design, barely more than a toy, and rebuilt it. Stronger lenses, better grinding, a longer tube. He created a telescope that magnified objects roughly 20 times. Then, on a cold January night in 1610, he turned it toward the sky, and the universe cracked open. What he saw through that narrow tube of glass and metal shattered 2,000 years of careful observation. Hipparchus had counted roughly 1,000 stars. Galileo, in a single evening, saw thousands more, faint stars packed between the bright ones. Stars where there should have been darkness. The heavens, it turned out, had been hiding most of themselves all along. Imagine being the first human to see this. You've spent your whole life trusting your eyes. The sky has always been what it appears to be, a dome sprinkled with visible lights, maybe 6,000 total, if you're patient and the night is clear. Then you press your eye to a crude telescope, and suddenly there are 10,000 stars, 20,000. So many you can't count them fast enough. They crowd the eyepiece. They blur together in dense patches. The Milky Way, that faint cloudy band you've always wondered about, resolves into individual stars. Thousands upon thousands of them. It's not mist. It's not milk spilled by a goddess. It's stars all the way down, stars layered on stars. Stars so distant and dim, they merge into a glow. It's overwhelming, exhilarating, terrifying. Galileo's first observations were of Jupiter. On January 7th, 1610, he noticed 3 small stars arranged in a straight line near the bright planet. The next night, they'd moved. A 4th appeared. Within a week, he realized these weren't stars at all. They were moons orbiting Jupiter, 4 worlds circling another world. This was heresy to the prevailing Aristotelian cosmology, which insisted everything in the heavens orbited Earth. But here was direct evidence of a different center, a different system. Scientists suggest this discovery, Jupiter's 4 Galilean moons, as we call them now, did more to validate the Copernican model than any mathematical argument could. You can debate philosophy. You can't debate what you see with your own eyes. But it was his observations of the Milky Way that truly multiplied the stars. Galileo published his findings in a slim book called Sidereus Nuncius, the Starry Messenger. In it, he described how the telescope revealed stars in such numbers as almost to surpass belief. He pointed his instrument at the constellation Orion and counted over 500 stars, where the naked eye saw only about 80. He looked at the Pleiades star cluster, traditionally visible as 6 or 7 sisters, and found over 40 stars packed into that small region. Everywhere he looked, the sky teemed with hidden lights. Some of these stars were simply fainter versions of what Hipparchus had catalogued magnitude 7, 8, 9 stars that human eyes couldn't quite detect. But others were fundamentally different. Nebulae, fuzzy patches that ancient astronomers had noted but couldn't explain. Galileo turned his telescope toward the Praesepe cluster in Cancer, known to the naked eye as a hazy blur. Through the lens, it exploded into a swarm of more than 40 distinct stars. The Orion Nebula, visible as a smudge in Orion's sword, revealed itself as a dense knot of starlight. He didn't fully understand what he was seeing. He thought all nebulae were just distant star clusters. But he was right about one thing. The universe was far more populated than anyone had imagined. Here's where the psychology gets interesting. For 2 millennia, humans had believed the stars were countable. Difficult to count, yes. Time-consuming. But finite. Knowable. Hipparchus counted 1,000. Later, astronomers added a few hundred more. But the number felt manageable. The cosmos felt comprehensible. Galileo destroyed that comfort. His telescope suggested that for every visible star, there might be 10 or 100 hidden ones. And if that was true, how many stars were truly out there? Thousands, tens of thousands, millions. The question that had once seemed answerable suddenly became infinite. And yet, Galileo's telescope was primitive by modern standards. His best instrument magnified about 20 to 30 times. The optics were crude chromatic aberration turned bright stars into rainbow halos. The field of view was tiny, like looking through a drinking straw. He had to sweep the telescope slowly across the sky, memorizing patterns, sketching what he saw before the Earth's rotation carried it out of view. There was no camera, no way to record an image, just his eye, his hand, and his notebook. Despite these limitations, he saw enough to know the old counts were hopelessly wrong. Let's talk about the mistake almost everyone made after Galileo, a misunderstanding that persisted for another century. Many astronomers assumed the Milky Way was simply a flat disk of stars, and that if you could see it edge on, it would look like a band across the sky. That part was correct. But they also thought the solar system sat near the center of this disk. After all, the Milky Way looked roughly the same brightness in all directions, which suggested we were equidistant from its edges. Seems logical, right? If you're sitting in the middle of a circular room, the walls appear equally far away in every direction. But the assumption was wrong. The Milky Way isn't uniform. Dust clouds block light from the galactic center, making it look dimmer. The disk is warped and irregular. We're actually about 2/3 of the way out from the center, roughly 26,000 light-years from the galactic core. But Galileo couldn't know that. He just knew there were more stars than anyone had counted. One of the most persistent questions Galileo faced was about stellar parallax. If Earth really orbits the Sun, as Copernicus claimed, then nearby stars should appear to shift position relative to distant stars. As we move from one side of our orbit to the other 6 months later, it's the same effect you see when you hold your finger in front of your face and close one eye, then the other. Your finger seems to jump against the background. Astronomers searched for this stellar parallax and found nothing. Critics used this as evidence against the heliocentric model. Earth must be stationary, they said, because the stars don't move. But Galileo understood the real reason. The stars were so absurdly distant that their parallax was too small to measure with the instruments of his time. Even the nearest stars, Alpha Centauri, Sirius, Procyon, are light years away. Their parallax shifts are measured in fractions of an arcsecond angles so tiny, you'd need telescopes far better than anything available in the 17th century. Stellar parallax wasn't successfully measured until 1838, when Friedrich Bessel detected the tiny wobble of 61 Cygni. By then, Galileo had been dead for nearly 200 years. But he was right. The universe wasn't small and cozy. It was vast and empty and filled with distant suns. Research shows that Galileo's early telescopes could detect stars down to about magnitude 9 or 10 under good conditions. That's roughly 60 times fainter than the naked eye limit. Doesn't sound like much, does it? But it increased the number of visible stars from about 6,000 to over 30,000. A five-fold increase just from improving the light-gathering power of the human eye by a factor of 60. Imagine what that meant psychologically. The universe had suddenly become 5 times larger. And if a crude telescope could do that, what would happen with better instruments? The implication spiraled outward. If there were 30,000 stars visible with Galileo's telescope, maybe there were hundreds of thousands beyond that. Millions, billions. Where did it end? It didn't end. That was the unsettling revelation. The universe might be infinite or so large that infinity and finite were functionally the same. This idea terrified some people and exhilarated others. The philosopher Giordano Bruno had suggested decades before Galileo that the stars were distant suns, each possibly surrounded by planets, each possibly hosting life. The church burned him at the stake in 1600 for this and other heresies. Galileo was more careful. He reported what he saw without speculating too wildly about its implications. But the implications were there, hanging in the cold January air, every time he pointed his telescope upward. We are not central. We are not unique. We are one world among many orbiting one star among multitudes. Have you ever felt that mix of smallness and wonder? That feeling when you realize you're part of something incomprehensibly large? It's humbling, yes. But there's also a strange comfort in it. Your problems shrink when you remember the scale of things. The universe doesn't care about your mistakes, your fears, your daily anxieties. It just keeps expanding star after star, galaxy after galaxy, indifferent and eternal. And somehow knowing that makes it easier to breathe. Galileo also made an error that's worth mentioning. He believed the stars were all roughly the same intrinsic brightness, just like Hipparchus had. Some appeared brighter because they were closer, some dimmer because they were farther away. It seemed reasonable, but stars vary wildly in luminosity. A red dwarf like Proxima Centauri emits about 0.17% of the sun's light. A blue supergiant like Rigel pumps out over 100,000 times the sun's luminosity. If you place them at the same distance, Rigel would outshine Proxima by a factor of millions. Galileo didn't know this. Neither did anyone else for another 2 centuries. It's a reminder that even revolutionary discoveries come wrapped in misconceptions. You can be right about the big picture and wrong about the details. Progress isn't a straight line. The telescope also revealed something Galileo found deeply puzzling. Stars, even magnified, remained point sources of light. Planets grew into visible disks. He could see the phases of Venus, the rings of Saturn, though he misinterpreted them as handles. But stars stayed sharp and tiny, no matter how much he magnified them. Why he assumed it was a limitation of his optics. In reality, stars are so distant that even through modern telescopes, most remain unresolved points. Their angular size is measured in milliarc seconds, far too small for any optical telescope on Earth to resolve. The only stars we can see as actual disks are nearby giants like Betelgeuse, and even then, only with interferometry or space-based instruments. Galileo was seeing the universe as it truly is, vast distances reducing suns to pinpricks. One more thing about Galileo's observations. He noticed that stars' twinkle scintillated in technical terms, but planets didn't, or at least not as much. Why? The atmosphere. Turbulence in Earth's air causes starlight to shimmer and dance. Planets, being extended disks rather than points, average out the scintillation. Each tiny part of the planet's disk scintillates slightly out of phase with the others. So, the overall effect is steadier light. Galileo used this as a way to distinguish stars from planets. It's still a useful trick for amateur astronomers. If it twinkles, it's a star. If it glows steadily, it's probably a planet, or a satellite, or an airplane, but usually a planet. By the time Galileo died in 1642 under house arrest for his defiance of the church, the old cosmology was dying too. The Earth wasn't the center, the stars weren't painted on a sphere. The universe was bigger, stranger, and more magnificent than scripture or philosophy had allowed. And all because of a tube with two lenses. It seems almost absurd, doesn't it? That such a simple tool could change everything. But that's how progress works. Not through grand revelations descending from on high, but through small improvements compounding, a better lens, a longer tube, a willingness to look at what everyone else had ignored. Galileo multiplied the stars from thousands to tens of thousands. But even he couldn't have imagined what would happen when telescopes grew larger, when mirrors replaced lenses, when observatories were built on mountaintops far from city lights. The count would keep growing. The universe would keep expanding in our awareness. And every new generation of astronomers would discover that the previous generation had barely scratched the surface. The stars weren't just numerous. They were innumerable. And yet, we'd keep counting. Because that's what we do. We measure the immeasurable. We name the infinite. One star, one galaxy, one cosmic revelation at a time. But as telescopes improved and the star count climbed into the hundreds of thousands, a new question emerged. Not just how many stars, but how are they arranged? Do they scatter randomly across space, or is there a structure, an architecture? And to answer that, we needed someone willing to spend decades mapping the sky with obsessive precision. Bath, England, 1773. A German musician named Friedrich Wilhelm Herschel is making a comfortable living playing oboe and conducting concerts. He's recently anglicized his name to William. He teaches music lessons, composes symphonies, performs for wealthy patrons. By all accounts, he should be content. But at night after the concerts end and the candles burn low, he feels pulled towards something else, the sky. He reads books on astronomy. He learns to grind lenses. And slowly, obsessively, music becomes secondary to a new passion. He decides he's going to map the entire heavens, not just count the stars, understand their arrangement, their structure, the architecture of creation itself. This is the beginning of one of astronomy's most ambitious projects. For the next 4 decades, William Herschel and his sister Caroline would spend thousands of nights sweeping the sky, cataloging stars, nebulae, and strange fuzzy objects no one had properly studied before. They would discover a planet Uranus and fundamentally reshape how humanity understood the Milky Way. But they would also make mistakes. Beautiful, instructive mistakes that reveal just how hard it is to see the universe clearly, even when you're staring right at it. William started small. He bought telescopes, found them inadequate, and began building his own, grinding mirrors by hand in his basement, polishing metal until it gleamed. His first serious instrument had a 6-inch mirror, then 9 inches, then 12. Each improvement gathered more light, revealed fainter stars, pushed deeper into space. But William wanted more. He wanted a telescope so powerful it could see to the edge of the universe if such an edge existed. So in 1789, with funding from King George III, he completed his masterpiece, a 40-foot-long telescope with a mirror 4 feet across. It was a monster. A cathedral of metal and wood towering over his backyard in Slough. Neighbors thought he was mad. Maybe he was, but he could see things no one else could. On clear nights, William would climb into the observing platform, position himself at the eyepiece, and slowly sweep the telescope across narrow strips of sky. Caroline sat below, with notebooks recording everything he shouted down: star positions, brightness estimates, nebulae, clusters, strange objects that didn't fit any known category. It was methodical, exhausting work. Research shows that over the course of his career, Herschel cataloged over 2,500 nebulae and star clusters, more than all previous astronomers combined. He also counted stars in different regions of the sky, trying to determine the shape and extent of what he called the sidereal system. We'd call it the Milky Way galaxy. His method was clever. He divided the sky into regions and counted how many stars appeared in each direction at various brightness levels. If the Milky Way was shaped like a disk, he reasoned you'd see more stars when looking along the plane of the disk, edge-on through the thickness, and fewer when looking perpendicular to it. And that's exactly what he found. The Milky Way wasn't a sphere. It was a flattened structure like a lens or a grindstone. He sketched it in his notes, a wide, flat disk of stars with the sun somewhere near the center. It was the first real model of our galaxy's shape, and it was both brilliant and completely wrong in one critical way. Here's the error. Herschel assumed he could see to the edge of the Milky Way in every direction. If he looked toward a region with fewer stars, he thought that meant the boundary of the galaxy was closer in that direction. If he saw dense star fields, the edge must be farther away. Seems logical. But he didn't account for something invisible: dust. Vast clouds of interstellar dust scattered throughout the galaxy, blocking light from distant stars. When Herschel looked toward the galactic center toward Sagittarius, dust obscured most of the stars. It looked sparse, so he assumed the edge of the galaxy was nearby. In reality, the galactic core lay in that direction, hidden behind curtains of cosmic soot. He couldn't see it, so he assumed it wasn't there. This mistake led him to conclude that the sun sat near the center of the Milky Way. Why wouldn't it? The distribution of visible stars seemed roughly symmetrical around us. We appeared to be in the middle of things. It's the same error ancient astronomers made when they placed Earth at the center of the universe. We see from where we stand, and it's hard to imagine we're not in the middle. The truth that our sun is a nondescript star about 26,000 light years from the galactic center, 2/3 of the way out in a spiral arm, wouldn't be discovered for another century. Herschel lacked the tools to detect his error. No amount of counting stars could reveal what dust was hiding. But let's not dwell only on mistakes. Herschel's discovery of Uranus in 1781 was pure, unambiguous triumph. He was conducting one of his systematic sweeps when he noticed an object that didn't look quite like a star. It was slightly fuzzy extended. Over several nights it moved against the background stars. At first he thought it might be a comet, but its orbit was nearly circular, not elliptical like most comets. Calculations revealed the truth. This was a planet, the first planet discovered in recorded history. Mercury, Venus, Mars, Jupiter, and Saturn had been known since antiquity. They were just their obvious wanderers in the sky. But Uranus required a telescope to see. It was magnitude 5.5, at best, right at the edge of naked eye visibility under perfect conditions, but too faint for ancient astronomers to notice. The discovery made Herschel famous overnight. King George gave him a pension. He quit music entirely and devoted himself to astronomy, and Uranus itself doubled the known size of the solar system. It orbits the sun at roughly 19 astronomical units compared to Saturn's 9. The solar system wasn't a cozy collection of planets huddling near the sun. It extended vast distances into cold, dark space. If there was one planet hiding out there, might there be others? The answer, of course, was yes. Neptune would be discovered in 1846, Pluto in 1930. The solar system kept growing, just like the star count. Herschel's obsession with counting stars led him to develop a concept called star gauges. He would point his telescope at a specific region and count every star visible in the field of view. Then he'd move to another region and count again. Over time, he built up a statistical map of star density across the sky. Some regions had hundreds of stars per square degree. Others had only a few dozen. The Milky Way band showed the highest density, confirming that most stars concentrated in a flat plane. But even in the darkest parts of the sky, away from the Milky Way, there were stars. Not as many, but they were there. This suggested the galaxy extended in all directions, though it was much thicker in the plane. Caroline Herschel deserves recognition here too. She wasn't just William's assistant, she was an astronomer in her own right. While William focused on star counts and nebulae, Caroline discovered 8 comets and compiled revised catalogs of star positions. She worked in freezing observatories recording data by candlelight, her fingers numb from cold. When William's giant 40-foot telescope proved too cumbersome for regular use, Caroline operated smaller instruments and conducted her own sweeps. She found nebulae William had missed. She corrected errors in previous catalogs. After William's death in 1822, she continued refining their work, publishing improved catalogs that astronomers used for decades. Yet history often reduces her to a footnote. She was the first woman to receive a salary as a scientist, the first woman to publish scientific papers in the journals of the Royal Society. But for a long time, her name appeared mostly in connection with her brother's achievements. That's changing now, slowly. We're learning to see collaborators where we once saw assistants. One of William's most ambitious attempts to count stars involved trying to estimate the total number in the Milky Way. He knew he couldn't count them all individually. There were far too many, and many were too faint even for his telescopes. So, he used statistics. He calculated the average number of stars in a given volume of space based on his star gauges, then estimated the volume of the Milky Way based on his incorrect model of its shape. His final estimate, somewhere around 100 million stars in the galaxy. Not bad for an 18th century calculation made without computers photography or an understanding of interstellar dust. The actual number is closer to 100 to 400 billion, so he was off by a factor of 1,000 or more. But the method was sound. Estimate what you can see, extrapolate to what you can't. It's the same basic approach astronomers use today, just with vastly better data. Herschel also grappled with the nature of nebulae, those fuzzy patches Galileo had noted. Some nebulae, when viewed through powerful telescopes, resolved into clusters of individual stars, the Pleiades, for instance. Precep. These were clearly groups of stars too distant or faint to distinguish individually with the naked eye. But other nebulae refused to resolve, no matter how much magnification Herschel applied. The Orion Nebula, the Andromeda Nebula. They stayed fuzzy, cloudy, indistinct. Herschel initially thought better telescopes would eventually resolve them into stars. But as his instruments improved and the nebulae remained nebulous, he began to suspect they might be something fundamentally different. Perhaps clouds of glowing gas, perhaps shining fluid, as he called it. He was right, at least partly. Some nebulae are gas clouds illuminated by nearby stars, but others, like Andromeda, are entire galaxies, island universes containing billions of stars so distant they appear as faint smudges. He couldn't have known that. The concept of galaxies beyond the Milky Way wouldn't solidify until the 1920s. So, Herschel did what any good scientist does when faced with ambiguity. He cataloged, categorized, and admitted uncertainty. He created classes of nebulae based on appearance. Some were round, some were elongated, some had stars embedded in them. He didn't pretend to understand them fully. He just recorded what he saw and trusted that future astronomers would figure it out. That's humility. That's rigor. Knowing the limits of your knowledge and documenting carefully so others can build on your work. Let's talk about the physical toll of this work. Herschel spent decades in unheated observatories, often in sub-freezing temperatures. He observed until dawn, slept a few hours, then spent the day grinding mirrors, repairing equipment, and analyzing data. His health suffered, his eyesight weakened, but he kept going. Why? What drives someone to sacrifice comfort, health, even sanity for a catalog of stars? Maybe it's the same thing that drove Hipparchus, the belief that understanding the universe matters, that knowledge is worth pursuing for its own sake, not for fame or wealth, but because not knowing is unbearable, because the stars are there shining every night, and someone has to count them, someone has to try. One fascinating aspect of Herschel's work is how he thought about the possibility of life elsewhere. He believed the sun and stars were inhabited, not by humans exactly, but by beings suited to their environments. He even speculated that there might be life on the sun living beneath a cool outer layer. Seems absurd now, but it was a reasonable hypothesis given what he knew. The sun emitted light and heat, yes, but maybe its surface was temperate habitable. He had no way to measure the sun's actual temperature around 5,500 degrees Celsius. At the surface, millions of degrees in the core. Spectroscopy. The tool that would reveal the sun's composition and temperature hadn't been invented yet. So, Herschel speculated. He imagined a cosmos teeming with life. Every star a sun. Every sun possibly surrounded by planets. Every planet possibly home to creatures gazing up at their own night sky, wondering the same questions. Do you find that idea comforting or unsettling? That we might not be alone, that somewhere orbiting some distant star, Herschel cataloged but never understood, there might be someone looking back, counting their own stars, asking their own questions about existence? Or does it make you feel even smaller, even more lost in the immensity? Maybe both feelings are true. Maybe that's okay. Herschel's 40-foot telescope, that towering monument to ambition, was eventually dismantled. The metal mirror tarnished, the wooden frame rotted. Technology moved on. Reflecting telescopes with silver-coated glass mirrors replaced speculum metal. Astrophotography replaced hand-drawn sketches, but Herschel's catalog survived. His nebulae became the NGC catalog, the new general catalog still used by astronomers today. NGC 224 is the Andromeda Galaxy. NGC 1976 is the Orion Nebula. Objects Herschel stared at through crude eyepieces are now photographed by space telescopes in exquisite detail. His work endures not because he got everything right, but because he got enough right to matter. He advanced the conversation. He pushed the boundary of knowledge just a little further out into the dark. The lesson here maybe is persistence. Herschel wasn't the most brilliant astronomer. He made significant errors. His model of the Milky Way was flawed. His belief in solar inhabitants was wrong, but he worked harder than almost anyone. He built better tools. He looked more carefully. He counted more stars. And in doing so, he transformed astronomy from a pastime of wealthy gentlemen into a rigorous data-driven science. He proved that systematic observation repeated thousands of times could reveal patterns invisible to casual glances, that the universe rewards patience and method. And as his career wound down, as his eyes weakened and his strength faded, the count stood at hundreds of thousands of stars, cataloged thousands of nebulae, noted one new planet discovered. The universe was larger than when he started, not because it had grown, but because he had looked more carefully. That's all science really is, isn't it? Looking carefully, measuring precisely, admitting error, trying again, building on what came before. Herschel stood on Galileo's shoulders, and soon others would stand on his. Each generation seeing a little further, counting a little higher, understanding a little more. But even Herschel's massive catalogs represented only a fraction of the stars. To count deeper to measure, farther astronomers needed something new. Not just bigger telescopes, but a way to measure distance. Because a star's brightness depends on two things: how much light it emits and how far away it sits. Without knowing distance, brightness is ambiguous, useless for counting, and solving that problem required someone willing to stare at thousands of photographic plates measuring the flicker of variable stars with inhuman patience. Cambridge, Massachusetts, 1893. A young woman named Henrietta Swan Leavitt graduates from what is now Radcliffe College with a certificate in astronomy. She's 25 years old, partially deaf from an illness in her youth, and about to enter a profession that doesn't quite know what to do with women. Universities won't hire female professors. Observatories won't let women use telescopes. But there's one job available, a peculiar position at Harvard College Observatory. They're hiring women to examine photographic plates of stars, to measure, to calculate, to spend hours hunched over glass images counting and cataloging with meticulous precision. The pay is 25 cents an hour less than a factory worker earns. The title is Degrading Computer, a human calculator. But Henrietta takes the job. And in doing so, she's about to hand humanity the ruler that measures the universe. The work sounds tedious beyond comprehension. Stacks of photographic plates, each one a glass negative capturing a small patch of sky. Thousands of stars frozen in silver halide emulsion. Henrietta's task was to examine these plates under magnification and measure the brightness of variable stars, stars whose light output changes over time. She would compare images taken days or weeks apart, note which stars had brightened or dimmed, and record the data in careful columns. Hour after hour, plate after plate. Some stars pulsed regularly like cosmic metronomes. Others flickered unpredictably. Her job was simply to measure and record, not to theorize, not to publish under her own name, just to be the observatory's eyes and hands turning observations into numbers that the male astronomers could then analyze and claim credit for. But Henrietta noticed something, a pattern hidden in the data, and it would change everything. The Harvard College Observatory, under director Edward Pickering, had embarked on an ambitious project to photograph the entire sky and catalog every star visible on film. They'd set up telescopes in both Massachusetts and Peru to capture both hemispheres. The resulting photographic plates numbered in the hundreds of thousands. No single person could analyze them all. So, Pickering hired a team of women, educated, meticulous, willing to work for low wages because few other scientific opportunities existed for them. They were called Pickering's harem, by some, a term as dismissive as it was cruel. But these women, Henrietta Leavitt, Annie Jump, Cannon, Williamina, Fleming, and others, did groundbreaking work. They classified stellar spectra, they discovered novae, they built databases that astronomers still use today. And they did it for pennies, rarely receiving the recognition they deserved. Henrietta focused on the Magellanic Clouds, two fuzzy patches visible in the southern sky. To the naked eye, they looked like detached pieces of the Milky Way. We now know they're satellite galaxies, small, irregular galaxies orbiting our own, roughly 160,000 and 200,000 light-years away. But in Henrietta's time, their nature was unclear. What mattered to her was that they contained hundreds of variable stars called Cepheids. These stars brightened and dimmed in regular cycles ranging from a few days to several weeks. Scientists suggest these pulsations occur because Cepheid stars expand and contract rhythmically their outer layers, breathing in and out as internal pressure and gravity battle for equilibrium. Henrietta measured 1,777 variable stars in the Magellanic Clouds. Tedious work. She noted the period of each star, how many days it took to complete one brightness cycle. She measured the maximum and minimum brightness, and then she plotted the data, period versus brightness. And there it was, a relationship, a clear, unmistakable pattern. The brighter the Cepheid, the longer its period. Faint Cepheids pulsed quickly, completing a cycle in a few days. Brilliant Cepheids pulsed slowly, taking weeks. The relationship was tight, almost linear on a logarithmic scale. Every star in the Magellanic Clouds followed the same rule. Why did this matter? Because all the stars in the Magellanic Clouds are roughly the same distance from Earth. Think of them as lights scattered across a distant city. Some streetlights are dim, some bright. but they're all approximately the same distance away from you, so the difference in brightness you see reflects their actual intrinsic luminosity. Henrietta realized that if period correlates with intrinsic brightness, then Cepheid variables are standard candles. Measure a Cepheid's period and you know its true luminosity. Compare that to how bright it appears from Earth, and you can calculate its distance. The math is simple. Brightness falls off with the square of distance. A star twice as far away appears 1/4 as bright. If you know a star's true luminosity and measure its apparent brightness distance follows directly. In 1912, Henrietta published her findings in a brief paper, The Period Luminosity Relationship for Cepheid Variables. It was just a few pages long, dry, technical, no grand claims. But astronomers recognized its significance immediately. This was the cosmic yardstick they'd been searching for. Suddenly, you could measure distances to any object containing Cepheid variables, star clusters, nebulae, anything. You just needed to find a Cepheid, measure its period, and calculate how far away it must be to appear as faint as it does. But there was a catch. Henrietta's relationship was relative, not absolute. She knew that longer period Cepheids were intrinsically brighter, but she didn't know how bright. To turn her discovery into an actual measuring tool, someone needed to calibrate it. Find Cepheids close enough that their distances could be measured by other means. Parallax, for instance, then use those to set the scale. That calibration work fell to other astronomers, most notably Harlow Shapley and later Edwin Hubble. But the foundation, the crucial insight, was Henrietta's. Let's pause and consider what was stolen from her. Henrietta Leavitt never received major recognition during her lifetime. She was never promoted beyond her position as a research assistant. She never earned more than a modest hourly wage. When she died of cancer in 1921 at age 53, her obituary in the Harvard Observatory newsletter was brief and perfunctory. 4 years later, a Swedish mathematician named Gösta Mittag-Leffler wrote to Harvard asking for Henrietta's address. He wanted to nominate her for the Nobel Prize in Physics. The reply came back she had died 4 years earlier. Nobel Prizes aren't awarded posthumously. The universe's ruler, its fundamental tool for measuring cosmic distances, was discovered by a woman paid 25 cents an hour, and she died without ever knowing how profoundly her work would reshape astronomy. Research shows that women in early 20th century science faced systemic barriers that male colleagues did not. They were excluded from faculty positions, denied access to observational telescopes, and paid a fraction of men's salaries for equivalent work. Many of their discoveries were published under their supervisors' names or credited to male colleagues. Henrietta's period luminosity relationship was sometimes called Leavitt's Law, but often it was just absorbed into the general toolkit of astronomy without attribution. Even today, textbooks sometimes discuss Cepheid variables as distance indicators without mentioning the deaf woman who spent years measuring them on glass plates in a basement office in Cambridge. But let's return to the science. How does a Cepheid variable actually work? Why does it pulsate? The mechanism involves something called the kappa opacity mechanism. Deep in a star's outer layers, helium atoms absorb radiation, heating up and ionizing. Ionized helium is more opaque to light than neutral helium, so radiation gets trapped, pressure builds, the star expands. As it expands, the helium cools, recombines, becomes transparent again. Radiation escapes, pressure drops. Gravity pulls the star back inward. The cycle repeats. Bigger, more luminous stars have deeper, more massive envelopes, so they pulsate more slowly. Smaller stars pulsate quickly. Hence the period luminosity relationship. It's a natural consequence of stellar physics encoded in the fundamental properties of matter and light. Henrietta measured all this indirectly just by comparing brightness on photographic plates. She didn't know about helium opacity or stellar pulsation mechanisms. She just saw the pattern and reported it. That's the beauty of empirical science, isn't it? You don't always need to understand why something happens to recognize that it does happen. The pattern comes first, the explanation follows, sometimes decades later. Using Henrietta's law, astronomers quickly began measuring distances to star clusters. Harlow Shapley used Cepheids and globular clusters to map the structure of the Milky Way. He found that these clusters weren't distributed evenly across the sky, most concentrated in one direction toward Sagittarius, and they were far away, tens of thousands of light years distant. Shapley realized these globular clusters formed a halo around the Milky Way's center, and since the sun wasn't at the center of that distribution, it couldn't be at the center of the galaxy. We were off to one side, far from the core. This was a second Copernican revolution. First, we'd learned Earth wasn't the center of the solar system. Now, we learned the solar system wasn't the center of the galaxy. We kept getting demoted, pushed further toward the periphery of existence. But the real revolution came in the 1920s when Edwin Hubble turned his telescope toward the Andromeda Nebula and found Cepheids there. He measured their periods, applied Leavitt's law, and calculated Andromeda's distance, over 900,000 light-years away, far beyond the known boundaries of the Milky Way. This meant Andromeda wasn't a nebula within our galaxy. It was a galaxy in its own right, an island universe. And if Andromeda was a separate galaxy, then all those other spiral nebulae scattered across the sky were probably galaxies too. The universe once again had multiplied in size, and it all traced back to Henrietta's patient measurements of variable stars in the Magellanic Clouds. Have you ever wondered what it feels like to change the world without ever knowing it? Henrietta spent her days in a windowless office recording numbers, filling notebooks. She probably thought her work was important, but she couldn't have imagined that decades later, astronomers would use her discovery to measure the distance to galaxies billions of light years away, that the Hubble Space Telescope would identify Cepheids in galaxies so distant they appear as faint smudges, and use their periods to calculate distances accurate to within a few percent, that her name would be attached to a fundamental tool of cosmology. There's a cruel irony in how science often works. The people who do the hardest, most meticulous work, the measurers, the catalogers, the computers, are often forgotten, while those who interpret their data and publish grand theories receive fame. Henrietta gave astronomy the ruler. Others used it to measure the universe and won accolades. This isn't to diminish the work of Shapley, Hubble, or others. They made critical contributions, but the foundation they built on was Henrietta's, and for too long that foundation went unacknowledged. Modern astronomers have tried to correct this. Asteroid 5383 is named Leavitt in her honor. A crater on the moon bears her name. The American Association of Variable Star Observers awards the Henrietta Leavitt Prize for excellence in variable star research. But these are small gestures compared to the scale of her contribution. If there were justice in the universe, her name would be as famous as Galileo's or Newton's. Children would learn about the Leavitt Law in elementary school. But history is written by those with power, and Henrietta had none. Just her data, her pattern, her quiet, unshakable conviction that the numbers meant something. Let's talk about the technical limitations of her method because understanding them helps us appreciate how far astronomy has come. Henrietta's period luminosity relationship works beautifully for classical Cepheids, a specific type of yellow supergiant star. But there are other variable stars that pulsate for different reasons. RR Lyrae stars, for instance. W Virginis stars. They follow different period luminosity relationships. Early astronomers sometimes confuse them, leading to incorrect distance measurements. It took decades to sort out which stars were which to refine the calibration to account for interstellar dust that dims light and makes objects appear farther than they are. There's also the problem of metallicity. Stars with different chemical compositions pulsate slightly differently. A Cepheid, rich in heavy elements, behaves differently than one made mostly of hydrogen and helium. This affects the period luminosity relationship in subtle ways. Modern calibrations account for this, but Henrietta had no way to measure stellar composition. She worked with what she could see: brightness and time. That she extracted such a fundamental relationship from such limited data is remarkable. Another challenge: photographic plates aren't perfect brightness detectors. They respond non-linearly to light. Faint stars might barely register, while bright stars saturate the emulsion. Henrietta had to develop techniques to measure brightness accurately despite these limitations. She used comparison stars, stars of known brightness in the same field, to calibrate each plate. She measured star sizes on the negative, knowing that brighter stars created larger spots on the film. It was imperfect, error-prone, but it worked well enough to reveal the pattern. And consider the sheer volume of work. Henrietta examined tens of thousands of photographic plates over her career. Each plate required careful measurement under magnification, notes recorded in pen, data transferred to tables. No computers to automate the process. No digital images, just glass silver and human attention. The physical and mental toll must have been exhausting. Eye strain, headaches, the repetitive stress of bending over a light table for hours. And through it all, the knowledge that her male colleagues doing less tedious work earned far more and received far greater recognition. Yet, she persisted. Maybe because she loved the work. Maybe because she had no other options. Maybe because, like Herschel, like Hipparchus, she felt compelled to understand, to measure, to count. The stars didn't care about her salary or her gender. They pulsed with the same regularity whether a man or woman measured them. And in that regularity, Henrietta found something pure, something true, a relationship that transcended the social inequalities of her era. The period-luminosity relationship remains one of the cornerstones of modern cosmology. It's how we measure distances to nearby galaxies. It's how we calibrated the cosmic distance ladder, a series of overlapping methods for measuring greater and greater distances into the universe. Parallax for nearby stars. Cepheids for nearby galaxies. Type 1, supernovae for distant galaxies. Each rung depends on the one below it, and the second rung, the one that bridges from stars to galaxies, is Henrietta's. Without it, we'd still be arguing about whether the Milky Way constitutes the entire universe. Do you ever think about how much we owe to people we've never heard of? How many quiet contributors made the world we live in possible? Henrietta Leavitt didn't discover a planet. She didn't build a giant telescope. She measured brightness variations on photographic plates and noticed a pattern, that's all. But that pattern became a key. It unlocked distances, and distances let us map the universe, understand its scale, trace its expansion, measure its age. One woman, 25 cents an hour, working in obscurity. And the cosmos bent slightly, revealing itself more fully because she paid attention. There's a lesson there about value, about what society rewards and what it ignores, about who gets remembered and who gets forgotten. But there's also a lesson about the work itself. Henrietta couldn't have known her discovery would echo through a century of astronomy. She just did the work, measured carefully, trusted the data, let the pattern speak. And the pattern turned out to be one of the universe's most important sentences. As we drift deeper into this story, as the star count climbs from thousands to millions to billions, Henrietta's ruler stretches alongside it, measuring farther, reaching into darkness, pulling distant galaxies into focus. But even as distances grew clearer, a fundamental question remained murky. Just how big was the Milky Way? And was it everything, or just one island in an ocean of galaxies? That question sparked a confrontation between two astronomers, a debate that would define the next era of cosmic discovery. Washington, D.C., April 26, 1920. The National Academy of Sciences auditorium fills with some of the country's most distinguished astronomers, physicists, and intellectuals. They have gathered for what will become known as the Great Debate, though the participants themselves probably didn't realize they were making history. Two men, two presentations, One fundamental question: how big is the universe as the Milky Way? Everything the entire cosmos, with those mysterious spiral nebulae, just gas clouds swirling within it? Or is the Milky Way merely one island among countless others? Each spiral nebula, a separate galaxy floating in an ocean of darkness. The answer would redefine humanity's place in existence. And both sides, convinced of their correctness, were about to discover they were partially right and devastatingly wrong. On one side stood Harlow Shapley, a young astronomer from Missouri who'd built his reputation studying globular clusters using Henrietta Leavitt's Cepheid variable method. He'd measured distances to these dense spherical collections of stars and found they formed a vast halo around the Milky Way's center. His calculations suggested the galaxy was enormous, roughly 300,000 light-years across, far larger than anyone had previously thought. And because the Milky Way was so immense, Shapley argued those spiral nebulae scattered across the sky must be inside it. Just gas clouds, nothing more. The Milky Way was the universe. We lived in a cosmos of one galaxy, one vast structure containing everything that existed. Facing him was Heber Curtis, an older, more established astronomer from California. Curtis had studied spiral nebulae extensively. He'd photographed them, measured their spectra, noted novae exploding within them. And he'd come to a radical conclusion. These spirals weren't gas clouds. They were island universes, separate galaxies like our own, scattered through infinite space. The Milky Way, Curtis believed, was much smaller than Shapley claimed, perhaps 30,000 light-years across. And those spiral nebulae. They were distant, unreachable, each containing billions of stars. The universe, in Curtis's view, extended far beyond anything humans had imagined. We were one galaxy among multitudes, a drop in an endless ocean. The debate itself was oddly anticlimactic. Shapley spoke first, presenting a dense technical talk filled with data about globular clusters and galactic structure. He overwhelmed the audience with numbers. Curtis followed with a more accessible presentation, emphasizing photographs of spiral nebulae and their similarities to edge-on views of the Milky Way. There was no dramatic confrontation, no shouting match. Just two scientists presenting their interpretations of the data, politely disagreeing, then sitting down. The audience, expecting fireworks, got careful scientific argumentation instead. Many left confused about who had won, but the debate's significance wasn't in that single evening. It was in what it represented: a turning point. A moment when astronomy stood at the edge of a conceptual cliff, about to fall into a much larger universe. And the fascinating thing, both men were right about some things, and wrong about others. Shapley was correct that the Milky Way was larger than previously thought, and that the Sun wasn't at its center. But he was wrong about the spiral nebulae. Curtis was correct that spiral nebulae were separate galaxies, but he underestimated the Milky Way's size. The truth, as is often the case, lay somewhere between their positions. Let's examine Shapley's evidence. He'd used Cepheid variables and globular clusters to calculate their distances. These clusters, he found, weren't scattered randomly. They concentrated in one hemisphere of the sky toward Sagittarius. And they were far away, 30,000, 50,000, even 100,000 light-years distant. If these clusters formed a halo around the galaxy's center, and they were that far away, the galaxy itself must be enormous. Shapley calculated a diameter of roughly 300,000 light-years. That's actually too large. The modern estimate is closer to 100,000 light-years, but it was in the right ballpark. He'd correctly deduced the galaxy's basic structure: a flat disk surrounded by a spherical halo of globular clusters. And he'd correctly placed the Sun far from the center, about 2/3 of the way out. This was a huge leap forward. For centuries, astronomers had assumed the Sun sat near the galaxy's center because the Milky Way band looked roughly the same in all directions. But Shapley realized this was an illusion caused by interstellar dust. Looking toward the galactic center, we can't see very far because dust blocks the view. Looking away from the center, we can see farther, but there are fewer stars. The two effects roughly cancel out, creating the illusion of centrality. Shapley saw through this. He used globular clusters, which orbit above and below the dusty galactic plane, to map the galaxy's true structure. Brilliant detective work. But then he made a critical error. He looked at spiral nebulae like Andromeda and argued they must be inside the Milky Way. Why? Partly because of a measurement made by Dutch astronomer Adrian van Manen. Van Manen claimed to have detected rotation in spiral nebulae. He measured changes in the position of features within the spirals over a period of years. If the spirals were rotating fast enough to detect motion over such a short time, and if that motion was measurable with telescopes, then they couldn't be very far away. Distant objects wouldn't show perceptible motion over human timescales. Therefore, spiral nebulae must be relatively nearby, inside the Milky Way. Case closed. Except Van Manen was wrong. His measurements were an artifact of his technique. Research suggests he was unconsciously biased by his expectation of finding rotation, and he introduced systematic errors in his photographic plate measurements. Later, astronomers using better methods found no detectable rotation in nearby spiral galaxies over human timescales. They're simply too distant. A galaxy 2 million light-years away could be spinning, but we'd need centuries or millennia to detect the motion. Van Manen's data was faulty, but Shapley trusted it. And that trust led him to the wrong conclusion about spiral nebulae. Curtis, meanwhile, had different evidence. He'd observed novae stellar explosions in spiral nebulae like Andromeda, and he noticed these novae were much fainter than novae in the Milky Way. If novae in general have similar intrinsic brightness, if they're standard candles like Cepheids, then the faint novae in Andromeda must be very distant, hundreds of thousands of light-years away at least, too far to be inside the Milky Way. Curtis also noted that spiral nebulae avoided the plane of the Milky Way. They clustered near the galactic poles away from the disk. Why would gas clouds inside the galaxy avoid the galactic plane? It made more sense if they were external objects distributed randomly through space, but appearing to avoid the Milky Way's dusty disk, because dust obscured the ones lying in that direction. Curtis also pointed out similarities between spiral nebulae and edge-on views of what the Milky Way might look like from outside. Same flat disk shape, same central bulge, same spiral arms visible in some orientations. Wasn't it more parsimonious to assume these objects were the same type of structure as our own galaxy, just viewed from different angles and distances? Occam's razor suggested yes. But Curtis lacked definitive proof. His arguments were logical, but circumstantial. Here's what neither man knew in 1920. Andromeda contains roughly 1 trillion stars. It's about 5 million light-years away. Even with the best telescopes available in 1920, individual stars in Andromeda were mostly invisible. Only the very brightest supergiants and novae could be detected. Cepheids were just barely at the limit of detection. Within a few years, Edwin Hubble would identify Cepheids in Andromeda using the new 100-inch Hooker telescope at Mount Wilson. He'd apply Leavitt's period luminosity law and calculate Andromeda's distance, and the debate would be settled. Curtis was right. Spiral nebulae were galaxies. The universe was vastly larger than Shapley imagined. But let's appreciate Shapley's predicament. He'd done careful, rigorous work measuring the Milky Way's size. His data was solid. His conclusions about galactic structure were correct. But he trusted Van Manen's rotation measurements, and the trust poisoned his reasoning about spiral nebulae. It's a reminder that science advances not just through good data, but through skepticism. Trusting the wrong measurement, even one made by a respected colleague, can lead you astray. Shapley should have been more critical. He should have questioned Van Manen's results. But hindsight is easy. At the time, Van Manen's measurements seemed plausible. Curtis, on the other hand, was working more from intuition and parsimony than hard data. He looked at photographs and thought, These spirals look like galaxies. He noticed patterns, the avoidance of the galactic plane, the faintness of novae, and inferred distance. His reasoning was sound, but he lacked the definitive measurement that would prove him right. That measurement, Hubble's Cepheids and Andromeda, was still a few years away. So Curtis argued his case based on likelihood and analogy, less rigorous than Shapley's approach, but ultimately closer to the truth. What's fascinating is how the debate energized astronomy. Suddenly, the field was alive with controversy. Everyone had an opinion. Observatories focused their telescopes on spiral nebulae, trying to settle the question. Photographic techniques improved. Larger telescopes were built. The pressure to resolve the debate drove technological and methodological advances. In that sense, both Shapley and Curtis contributed enormously, not by being right, but by framing the question in a way that demanded an answer. Do you ever find yourself in disagreements where both sides have valid points, where the truth isn't a simple binary, but a complex synthesis? The Great Debate was one of those moments. Shapley wasn't a fool. Curtis wasn't just guessing. They were both brilliant astronomers interpreting ambiguous data. And ambiguity in science is often resolved not by argumentation, but by better observations. You can debate interpretations endlessly, but eventually someone builds a better telescope, gathers clearer data, and the answer emerges. Let's talk about what the debate reveals about scientific progress. Science textbooks often present discoveries as smooth narratives. Someone asks a question, gathers data, and arrives at the correct answer. But real science is messy. It's debates like this. It's trusting the wrong colleague. It's being right about one thing and wrong about another. It's uncertainty stretching for years, sometimes decades before resolution. Shapley and Curtis didn't shake hands after the debate and agree on a compromise. They both went back to their observatories convinced they were right, and they stayed convinced until Hubble's data forced a resolution. The Great Debate also highlights the role of technological limits. Both men were constrained by the telescopes available in 1920. Neither could resolve individual stars and distant spiral nebulae. Neither could measure redshifts with precision. Neither could detect the faint Cepheids that would settle the distance question. They were working at the edge of what was observable. And when you're at that edge, interpretation becomes everything. Two astronomers can look at the same fuzzy photograph and see completely different things. One sees a gas cloud, the other sees a galaxy. Both are extrapolating beyond what the image actually shows. And both are in their own way making educated guesses. This is why replication and independent verification matter. Van Maenen's rotation measurements should have been checked by multiple observers before everyone accepted them. But astronomy, especially in that era, was often a solitary pursuit. One person made a measurement. Others trusted it. There wasn't always the infrastructure for large-scale collaborative verification. Today we have better safeguards. Data is shared openly. Multiple teams analyze the same observations. Systematic errors get caught more quickly. But mistakes still happen. We're still human. We still see what we expect to see sometimes. Another lesson from the debate: humility. Shapley, despite being wrong about spiral nebulae, maintained his confidence. He was certain Van Maenen was right, certain the Milky Way was the entire universe. Curtis was more tentative. He presented his evidence but acknowledged uncertainty. In the end, Curtis's humility served him better. He was open to new data. Shapley, perhaps more emotionally invested in his grand vision of an enormous Milky Way containing everything, resisted the evidence longer. When Hubble's data came in, Shapley had to accept he'd been wrong. To his credit, he did accept it. He didn't dig in defensively, but the process was painful. The debate also reminds us that truth doesn't care about eloquence or reputation. Shapley was the rising star, the brilliant young astronomer everyone was watching. Curtis was older, more methodical, less flashy. If scientific truth were decided by charisma or fame, Shapley would have won. But the universe doesn't work that way. Curtis's unglamorous, careful analysis of photographic plates turned out to be more accurate than Shapley's confident calculations. Sometimes the quiet voice in the room is the one worth listening to. After the debate, astronomy entered a new phase. The question wasn't just, how many stars anymore? It was, how many galaxies? If Andromeda was a galaxy and those thousands of other spiral nebulae were two, then the universe contained billions of galaxies each with billions of stars. The count hadn't just increased, it had exploded. The Milky Way's 100 billion stars became a tiny fraction of the cosmic total. Humanity shrank again. We weren't just off-center in our galaxy. Our entire galaxy was unremarkable, one among innumerable others scattered through a space so vast it defied comprehension. And there's something almost poetic about the debate's timing. April 1920. The world was recovering from the Great War. The influenza pandemic had just ended. Humanity was battered, exhausted, questioning everything. And in that moment of fragility, two astronomers argued about whether the universe was the Milky Way alone or something infinitely larger. The debate was technical, esoteric, but it touched something deeper, a need to know our place, to understand whether we mattered or were merely cosmic dust. The answer emerging over the next few years was humbling. We were smaller than we thought, but we were also part of something grander, part of a universe so vast that even being insignificant was somehow magnificent. Shapley and Curtis gave us a framework for asking the right questions. They forced astronomy to confront its assumptions. And while neither man fully understood the universe's true scale together, they pushed the boundary of knowledge outward. Shapley mapped the Milky Way. Curtis glimpsed the galaxies beyond. And within a few years, their debate would be rendered obsolete by new data, showing a universe even larger and stranger than either man imagined. But that data required someone willing to sit night after freezing night at a telescope on a California mountaintop, photographing faint fuzzy patches, measuring positions with micrometer precision, and finally, after years of effort, finding the evidence that would settle the question once and for all. Mount Wilson, California, October 1923. The night air is thin and cold at 5,700 feet above sea level. Edwin Hubble, a former lawyer turned astronomer, climbs into the observing cage of the 100-inch Hooker telescope, the largest telescope in the world at the time. He spent countless nights here photographing spiral nebulae, searching for something specific, variable stars, Cepheids if he's lucky. Because if he can find Cepheids in Andromeda and measure their periods, he can calculate the nebula's distance. And if that distance is large enough, it will prove Andromeda lies far beyond the Milky Way. It will prove Curtis was right. The universe is bigger than anyone dared imagine. Tonight, after examining a new photographic plate of Andromeda, Hubble will write a single word in pencil on the glass, VAR, variable star. And with that notation, the universe will change forever. Edwin Hubble didn't start as an astronomer. He studied law at Oxford as a Rhodes Scholar, returned to the United States, practiced briefly, and hated it. The law felt small, confined, suffocating. He wanted something larger. So at age 25, he abandoned his legal career and enrolled in graduate school to study astronomy at the University of Chicago. His colleagues thought him arrogant. He affected a British accent, smoked a pipe, dressed impeccably. He carried himself with a confidence that bordered on cockiness. But he could back it up. He had sharp eyes, sharper instincts, and access to the best telescope on Earth. And he was willing to work harder than almost anyone. The 100-inch Hooker telescope was a marvel. Completed in 1917, its massive mirror gathered enough light to see fainter objects than any previous instrument. It could resolve details in spiral nebulae that smaller telescopes rendered as fuzzy blurs. Hubble spent night after night photographing Andromeda, exposing plates for hours to capture the faintest stars. The work was grueling. Winter nights at the observatory could drop below freezing. The dome was unheated. Observers wore heavy coats and gloves, their breath visible in the lamplight. But discomfort was irrelevant. What mattered was the data. What mattered was pushing deeper into space. On that October night in 1923, Hubble found three variable stars in Andromeda. Three Cepheids, their brightness fluctuating with regular periods. He measured their light curves graphs of brightness over time and applied Henrietta Leavitt's period luminosity relationship. The calculations were straightforward. Longer period meant greater intrinsic luminosity. Compare intrinsic to apparent brightness, and distance follows. The result stunned him. Andromeda was roughly 900,000 light-years away. Later refinements would push that number to over 2 million light-years, but even Hubble's initial estimate was enough. Andromeda wasn't inside the Milky Way. It couldn't be. The Milky Way was perhaps 100,000 light-years across. Andromeda lay far beyond its boundaries. Curtis had been right. Spiral nebulae were galaxies, island universes, and the cosmos had just multiplied in size by an unimaginable factor. Hubble announced his discovery in 1924. The astronomical community reacted with a mix of excitement and shock. Shapley, who'd argued against the island universe theory, had to concede. The evidence was irrefutable. Andromeda was a galaxy, and if Andromeda was a galaxy, then so were the thousands of other spiral nebulae scattered across the sky. Each one contained billions of stars. Each one sat millions or tens of millions of light-years away. The Milky Way, once thought to encompass everything, was suddenly just one galaxy among countless others. Humanity's cosmic address expanded. We lived on a planet orbiting a star, in a galaxy that was merely one of many. The demotion was complete. But Hubble wasn't finished. He'd opened the door to extragalactic astronomy. Now he walked through it. He began measuring distances to more galaxies. Some were closer, like the Small and Large Magellanic Cloud satellite galaxies orbiting the Milky Way at distances of around 200,000 light-years. Others were more distant. The Triangulum Galaxy, the Sombrero Galaxy. Each measurement pushed the boundary of the known universe outward. And as he gathered more data, he noticed something strange, a pattern. The farther away a galaxy was, the faster it seemed to be moving away from us. How did he measure this motion? Through something called redshift. When an object moves away from you, the light it emits stretches to longer, redder wavelengths. It's the same principle as the Doppler effect. With sound, a siren drops in pitch as an ambulance speeds away. With light, motion creates a shift in spectral lines. Scientists suggest this happens because the waves compress when an object moves toward you and stretch when it moves away. By measuring how much a galaxy's spectral lines shifted toward the red end of the spectrum, Hubble could calculate how fast it was receding. And what he found was astonishing. Almost every galaxy he observed was redshifted. They were all moving away. And the most distant ones were moving fastest. In 1929, Hubble published a paper that would become a cornerstone of modern cosmology. He plotted galaxy distances against their recession velocities and found a linear relationship. Double the distance, double the velocity. Triple the distance, triple the velocity. This relationship, now called Hubble's law, suggested something profound. The universe was expanding. Not just galaxies drifting randomly through static space, but space itself, stretching, carrying galaxies along with it. The farther apart, two galaxies were the faster. The space between them expanded, creating the appearance of higher velocity. Think about that for a moment. Space isn't a fixed stage on which events unfold. It's dynamic, growing. Every second, the distance between distant galaxies increases, not because they're flying through space like rockets, but because the fabric of space itself is expanding. It's like dots on a balloon. As you inflate the balloon, the dots move apart. The farther apart two dots are, the faster they separate, even though neither dot is actually moving across the balloon's surface. That's the universe. An inflating balloon with galaxies as dots. And Hubble, through patient observation and careful measurement, had discovered the inflation. This discovery had staggering implications. If the universe is expanding now, it must have been smaller in the past. Trace the expansion backward and everything converges to a single point, a moment of beginning. Scientists would later call this the Big Bang, though that term wouldn't be coined until the 1950s. Hubble didn't speculate much about origins. He just reported the data. Galaxies were receding. The universe was expanding. The implications were for others to work out. But he'd given cosmology its foundation, a measurable, observable fact that any theory of the universe would have to explain. Of course, Hubble's initial measurements weren't perfect. He underestimated distances because he confused two types of Cepheid variables, classical Cepheids and type 2 Cepheids. They follow different period luminosity relationships, and Hubble didn't realize this. His distance to Andromeda was off by a factor of more than 2. Later, astronomers, particularly Walter Baade in the 1950s, corrected this error and recalibrated the cosmic distance scale. Andromeda jumped from 900,000 light-years to 2.5 million light-years. The universe doubled in size overnight. Or rather, our understanding of its size doubled. The universe itself had been that large all along. We'd just been measuring it wrong. This correction had a cascading effect. If Andromeda was farther than Hubble thought, then other galaxies were farther too. And if they were farther then, the universe was older. The Hubble constant, the rate of expansion, had to be revised downward. This gave the universe more time to expand to its current size. Early estimates based on Hubble's measurements suggested a universe only 2 billion years old, which was problematic because geologists knew Earth was at least 3 billion years old. The universe couldn't be younger than its planets. The corrected distances resolved this paradox. The universe was much older. Current estimates put its age at 13.8 billion years. Plenty of time for galaxies to form stars, to ignite planets, to cool life to emerge. Hubble's work also revealed the diversity of galaxies. He classified them into types based on their appearance. Spirals like Andromeda and the Milky Way, with graceful arms curving outward. Ellipticals, which were round or elongated blobs with no structure. Irregulars, which were chaotic and asymmetric. He created the Hubble sequence, sometimes called the tuning fork diagram, showing how galaxies range from smooth ellipticals to tightly wound spirals to loose open spirals. For decades, astronomers thought this sequence represented an evolutionary path that galaxies started as ellipticals and evolved into spirals. But we now know that's backward. Spirals can collide and merge, forming ellipticals. The sequence doesn't represent time. It represents different outcomes of galactic formation and interaction. Research shows that galaxies aren't static objects. They collide, they merge, they tear each other apart with tidal forces. The Milky Way and Andromeda are currently on a collision course. In about 4 billion years, they'll merge into a single larger galaxy, probably an elliptical. Our night sky will transform. Stars from both galaxies will intermingle. Some will be flung into intergalactic space. Others will spiral into the new galaxy's core. The sun will likely survive, though it might be tossed into a different orbit. But by then, the sun will be nearing the end of its life anyway, swelling into a red giant. The collision is just one more cosmic event in an endless chain of transformations. Hubble didn't know about galactic collisions. His telescopes weren't powerful enough to see the fine details that reveal ongoing interactions. But he suspected galaxies weren't eternal, unchanging objects. He saw irregulars that looked disrupted. He saw spirals with distorted arms. He noted that galaxies tended to cluster, grouping into collections of dozens or hundreds. The Milky Way belongs to the local group, a cluster containing about 80 galaxies dominated by Andromeda and the Milky Way, with dozens of smaller dwarf galaxies orbiting them. Hubble cataloged these clusters and suspected they were gravitationally bound. He was right. Galaxies don't drift alone through space. They congregate, and their interactions shape their evolution. One of Hubble's most significant contributions was simply expanding the scope of what astronomers studied. Before him, astronomy was mostly about stars and the Milky Way. After him, it was about galaxies, clusters, the large-scale structure of the universe. He opened a new field, extragalactic astronomy, the study of everything beyond our galaxy. And he did it with a combination of technical skill and stubborn persistence. Night after night, plate after plate, measurement after measurement. He trusted the data. He followed where it led. And when it led somewhere uncomfortable, a universe far larger and stranger than anyone expected, he didn't flinch. He reported it. There's a lesson there about courage. Not the physical kind, though. Sitting in a freezing observatory night after night takes its own form of bravery. But intellectual courage, the willingness to accept what the data shows, even when it contradicts everything you thought you knew. Hubble's measurements suggested the universe was expanding. That was bizarre, counterintuitive. It meant space itself was changing. But the redshifts were real. The relationship between distance and velocity was clear. So Hubble accepted it. He didn't try to explain it away or force the data to fit preconceptions. He let the universe speak. And what it said was, I'm bigger than you thought. I'm older than you imagined. And I'm still growing. Do you ever feel that way when you learn something new? That sudden vertigo? When your understanding of the world shifts? When something you thought was fixed turns out to be fluid? That's what Hubble gave the world in the 1920s. A new cosmology, a universe in motion. And the gift, though disorienting, was also liberating. We weren't trapped in a static, eternal cosmos. We were part of something dynamic, something with a history, something that began and would someday end, though, on timescales so vast they dwarfed human comprehension. Hubble's name became synonymous with cosmic exploration. When NASA launched a space telescope in 1990, they named it after him. The Hubble Space Telescope has since become one of the most productive scientific instruments ever built. It's photographed distant galaxies, measured cosmic expansion, discovered dark energy, revealed the universe's age, all extensions of Edwin Hubble's work, all building on the foundation he laid in those cold nights on Mount Wilson. He couldn't have imagined it, a telescope bearing his name orbiting Earth, seeing deeper into space than any ground-based instrument. But he would have appreciated the continuity. One generation building on the last, each pushing a little farther, each counting a few more stars, a few more galaxies adding to the grand tally. By the time Hubble died in 1953, the star count had exploded from Hipparchus's 1,000 to uncountable billions. A single galaxy like the Milky Way contains 100 to 400 billion stars. And there are at least 2 trillion galaxies in the observable universe, each with its own billions of stars. Multiply that out. The total number of stars in the observable universe exceeds the number of grains of sand on all of Earth's beaches. It's a number so large it loses meaning. 10 to the 24th power. A trillion. More stars than seconds have elapsed since Earth formed. More stars than heartbeats in every human who's ever lived combined. The question Hipparchus asked how many stars had an answer now. More than we can count. More than we'll ever count. An infinity for all practical purposes. And yet even this staggering number is just what we can see. The observable universe is limited by the speed of light. Light from distant galaxies takes billions of years to reach us. There's a horizon beyond which light hasn't had time to arrive since the Big Bang. What lies beyond that horizon, we don't know. Maybe more galaxies, maybe infinite galaxies. Maybe the universe repeats itself, or loops back, or branches into parallel versions. We can't see beyond the horizon, so we can't say. But it's possible, likely even, that the true number of stars is infinite. That somewhere out there beyond the reach of our best telescopes, stars continue to shine, forever, in all directions, without end. Hubble's expanding universe answered some questions and raised countless others. If space is expanding, what's it expanding into? What existed before the Big Bang? Will expansion continue forever, or will gravity eventually pull everything back together? These questions drove the next generation of astronomers, and answering them required new tools, not just bigger telescopes, but different kinds of observation. Space-based instruments, digital detectors, automated surveys that could photograph millions of stars in a single night. Somewhere above Earth, right now a satellite spins silently in the darkness. It's called Gaia. Launched in 2013, it orbits the Sun at a point called L2, about 1 million miles from Earth. Every second, its instruments measure the positions of thousands of stars, with precision so extreme it could detect a human hair from 1,000 miles away. In a single day, Gaia observes roughly 850,000 stars. Over its mission lifetime, it has mapped nearly 1.8 billion stars in our galaxy positions, brightnesses, colors, distances, motions. It's the most detailed census of the Milky Way ever attempted. And yet, even 1.8 billion stars represents less than 2% of the galaxy's total. The rest remain uncounted, hidden in dust, too faint to detect, or simply too numerous to catalog individually. We've come so far from Hipparchus and his 1,000 stars, but the task's still unfinished, still impossibly vast. The revolution in star counting didn't happen overnight. It accumulated slowly across decades as telescopes grew larger, detectors grew more sensitive, and computers learned to process data faster than any human could. In the 1990s, the Hubble Space Telescope began sending back images that stunned astronomers. Deep field images, photographs of tiny patches of sky exposed for days, revealing thousands of galaxies in areas that appeared empty to ground-based telescopes. One image, the Hubble Deep Field, taken in 1995, captured a region of sky about the size of a grain of sand held at arm's length. In that minuscule patch, Hubble found roughly 3,000 galaxies, each galaxy containing billions of stars. Multiply that across the entire sky, and the universe's scale becomes almost paralyzing. Every direction you look in every seemingly empty space there are galaxies. Billions of them, each one a Milky Way unto itself. But let's focus on our own galaxy first, because even counting the stars in the Milky Way is a monumental challenge. The galaxy is roughly 100,000 light-years across and contains between 100 billion and 400 billion stars, depending on whose estimate you trust. Why the uncertainty? Because most stars are invisible to us, not because they don't exist, but because they're blocked by dust, or they're too faint, or they're hidden behind brighter neighbors. Imagine trying to count trees in a forest while standing inside it. You can see the nearby trunks clearly, but deeper into the woods, trees overlap shadows, obscure distance blurs everything together. That's our situation in the Milky Way. We're inside it, surrounded by stars and dust, trying to count something we can't fully see. This is where projects like Gaia come in. Gaia doesn't just count stars, it measures their positions with extraordinary precision down to micro-arc seconds, which is roughly the angular size of a coin on the moon as seen from Earth. Why does precision matter? Because it allows astronomers to measure parallax. Remember parallax, that tiny apparent shift in a star's position when viewed from different points in Earth's orbit. Hipparchus couldn't detect it. Hubble barely could. But Gaia measures parallax for millions of stars, which gives us their distances. And knowing distance transforms everything. A faint star might be faint because it's distant or because it's intrinsically dim. Without distance, you can't tell. With distance, you can calculate a star's true luminosity, its mass, its age. You can build a three-dimensional map of the galaxy. You can trace how stars move, where they came from, where they're going. Gaia's third data release, published in 2022, included precise measurements for 1.8 billion stars. That's an almost incomprehensible number. If you counted one star per second, it would take you 57 years to count them all. And that's just the stars Gaia observed. Scientists estimate there are at least 100 billion more stars in the Milky Way that Gaia didn't detect, too faint, too obscured, or simply outside its field of view. The stars Gaia sees are mostly the brighter ones, the ones closer to us. The vast majority of stars are red dwarfs, small and dim, burning quietly for trillions of years. They vastly outnumber sun-like stars and giants, but they're much harder to detect. Many remain uncounted. Let's talk about methodology, because modern star counting is nothing like Hipparchus's approach. Instead of one person staring at the sky, it's automated telescopes, scanning systematically cameras, capturing digital images, algorithms analyzing the data. The Sloan Digital Sky Survey, which began in 2000, photographed over one-third of the sky and identified more than 500 million objects, stars, galaxies, quasars. It used a technique called drift scanning, where the telescope doesn't track objects across the sky. Instead, it stays fixed and lets Earth's rotation carry the sky through its field of view. The camera snaps images continuously like a photocopier scanning a page. Software then processes the images, identifies point sources, measures their brightness in multiple color filters, and catalogs everything automatically. This automation is crucial. A human astronomer examining photographic plates might catalog a few hundred stars in a good night's work. An automated survey can process millions. But automation introduces new challenges. Software makes mistakes. It might misidentify a cosmic ray hit on the detector as a star. It might overlook a faint star that falls below its detection threshold. It might blend two close stars into one. So, astronomers develop algorithms to minimize these errors using statistical methods and machine learning to distinguish real stars from artifacts. Even so, errors creep in. Catalogs contain ghost stars that don't exist, and miss real stars that do. The data improves with each iteration, but perfection remains elusive. Research shows that interstellar dust is one of the biggest obstacles to accurate star counting. Dust grains compose mostly of carbon, and silicates scatter and absorb starlight. A star behind a dense dust cloud might appear 10 times fainter than it actually is, or it might be invisible entirely. The galactic center, roughly 26,000 light-years away, in the direction of Sagittarius, is heavily obscured. We can barely see any stars there in visible light, but infrared light penetrates dust more effectively. Infrared telescopes like Spitzer and the James Webb Space Telescope can peer through the dust and reveal hidden stellar populations. This has revised our understanding of the galaxy's structure. Regions that appeared empty in visible light teem with stars in infrared. The count keeps rising. Distance is another challenge. Gaia's parallax method works well for stars within a few thousand light-years. Beyond that, the parallax becomes too small to measure accurately. For more distant stars, astronomers use other methods, spectroscopic parallax, where you infer distance from a star's spectrum, or statistical parallax, where you average over many stars. Each method has uncertainties. Errors compound. A star you think is 10,000 light-years away might actually be 8,000 or 12,000. That error affects everything downstream. Luminosity Calculations Age estimates the structure of the galaxy. Modern catalogs include error bars quantifying the uncertainty. But even with uncertainties, the data is orders of magnitude better than anything Herschel or even Hubble had. Let's compare Hipparchus's catalog to Gaia's. Hipparchus cataloged roughly 1,000 stars. Gaia has cataloged 1.8 billion. That's an increase of 1.8 million times. The precision has improved even more dramatically. Hipparchus measured positions to maybe 1 degree accuracy, about 2 full moon widths. Gaia measures positions to 20 microarc seconds, about the width of a human hair, seen from 1,000 miles away. The improvement is roughly 180 million times. That's what 2,000 years of technological progress looks like. Not gradual, steady improvement, but exponential acceleration. Telescopes, photography, digitization, space missions. Each innovation built on the last, and the pace keeps quickening. But here's the paradox. Despite cataloging 1.8 billion stars, we've only directly counted about 1 to 2% of the Milky Way's stars. The rest are inferred from models. Astronomers observe the stars they can see, note their distribution, and extrapolate. If this region contains X stars of a certain brightness and distance, and the galaxy is Y times larger than this region, then it probably contains roughly X times Y stars total. It's an educated guess refined by theory and observation, but still a guess. The true number could be 100 billion or 400 billion, or somewhere in between. We won't know exactly until we count them all, and that might never happen. Why not? Because some stars are simply too faint for current technology. A red dwarf, 50,000 light-years away, deep in the galactic halo, emits so little light that even our best telescopes can't detect it. We know such stars exist. We've seen plenty nearby, but we can't count the distant ones individually. We infer their existence statistically. Similarly, brown dwarfs, objects too small to sustain hydrogen fusion, bridging the gap between planets and stars, are extremely faint. Most remain uncounted. They could number in the billions lurking invisibly throughout the galaxy. The star count is incomplete, not because we're lazy, but because the universe hides many of its contents from view. Then there's the question of what counts as a star. Does a brown dwarf count? It doesn't fuse hydrogen, but it might fuse deuterium. Is that enough? What about white dwarfs, the remnants of dead stars, no longer fusing anything but still glowing from residual heat? What about neutron stars and black holes, the even denser remnants left after massive stars explode? Astronomers don't usually include these in star counts because they're not stars in the traditional sense. But they were stars once. Do past states count, or only current ones? These definitional questions matter when you're trying to arrive at a precise number. But for most purposes, when we say star, we mean main sequence stars, objects currently fusing hydrogen in their cores. That gives a clearer target, though, still an enormous one. Let's zoom out to the universe. If counting stars in the Milky Way is hard, counting stars in the observable universe is borderline absurd. But astronomers try. Here's the method. First, estimate the number of galaxies. Hubble Deep Field images suggest roughly 2 trillion galaxies in the observable universe. That number comes from counting galaxies in small patches of sky and extrapolating to the full sphere. Next, estimate the average number of stars per galaxy. The Milky Way has 100 to 400 billion. Some galaxies are smaller. Dwarf galaxies might have only a few billion stars. Others are larger giant ellipticals can have trillions. Average it all out, and you get roughly 100 billion stars per galaxy as a rough estimate. Multiply 2 trillion galaxies by 100 billion stars per galaxy, and you get 200 sextillion stars. That's 2 times 10 to the 23rd power. A 2 followed by 23 zeros. But that's just the observable universe, the part we can see limited by the speed of light and the age of the universe. Beyond that horizon, space continues, maybe forever. If the universe is infinite, then the number of stars is infinite too. We can't count infinity. We can only count what we can see. And even that is an estimate, a statistical projection based on samples and assumptions. The true number could be higher or lower, but it's definitely big. Incomprehensibly, overwhelmingly big. Do you ever feel the weight of that? The sheer scale. Every star a sun, some with planets, some of those planets possibly harboring life. Civilizations maybe. Other beings looking up at their own night sky, counting their own stars, wondering if they're alone. The numbers suggest we're probably not alone. With 200 sextillion stars, even if only a tiny fraction have habitable planets, and only a tiny fraction of those develop life, and only a tiny fraction of those develop intelligence, the sheer volume of opportunities means it's statistically likely we have company. But space is so vast and the distances so immense that we might never meet them. We might count their stars without ever knowing they're there. Modern surveys also revealed structure we didn't expect. Stars aren't scattered randomly. They cluster into galaxies. Galaxies cluster into groups and clusters. Clusters gather into superclusters, and superclusters arrange along filaments and walls, separated by vast voids where almost nothing exists. It's like a cosmic web with bright threads of galaxies and dark, empty spaces between them. The distribution is neither random nor uniform. It's structured, shaped by gravity, by dark matter, by the universe's expansion. Counting stars means understanding this structure, mapping it, modeling how it formed and evolved. One more piece of the modern puzzle: variability. Not all stars shine steadily. Some pulse like Henrietta's Cepheids. Others flare, suddenly brightening when magnetic activity triggers surface explosions. Eclipsing binaries dim periodically as one star passes in front of the other. Novae explode when white dwarfs pull material from companions. Supernovae blow apart entirely, briefly outshining their host galaxies. Counting these transient events adds another layer of complexity. A star that wasn't there yesterday appears today. Another disappears. The sky is dynamic, constantly changing, and any census is only valid for the moment it's taken. Modern missions like TESS, the Transiting Exoplanet Survey, satellite monitor hundreds of thousands of stars, continuously watching for brightness, changes that might indicate orbiting planets or stellar activity. Gaia updates its catalog with each data release, refining positions, discovering new stars, correcting old errors. The count is fluid, always improving, never final. And maybe that's fitting. The universe isn't static. Stars are born in nebulae, live for millions or billions of years, then die in various dramatic or quiet ways. The count changes constantly on timescales too slow for us to notice directly, but fast enough to matter on cosmic scales. So, where does this leave us? We've gone from Hipparchus's 1,000 stars to Gaia's 1.8 billion, from the Milky Way being the universe to it being one of 2 trillion galaxies. From no idea of distance to measuring parallax at microarc-second precision. The progress is staggering, but the task remains unfinished. Most stars in the Milky Way remain uncounted. Most galaxies in the universe remain unexamined. We've mapped a fraction, inferred the rest, and accepted that complete knowledge might be impossible. The universe is too big, too far, too hidden behind dust and distance. But we keep counting. We build better telescopes, we launch new satellites, we refine our methods, because the act of counting matters as much as the number. It's how we come to understand our place, our context, our cosmic address in the vast structure of everything. And as we've counted, we've found ourselves growing smaller and smaller until we're barely a speck. One planet among billions. One star among hundreds of billions. One galaxy among trillions. And yet, somehow we're the ones doing the counting. That has to mean something. 3,000 years. That's how long we've been trying to answer a single question. How many stars, from Hipparchus on his island, squinting at the Mediterranean sky, to Gaia spinning silently 1,000,000 miles from Earth, cataloging 1 billion points of light every few months. 3 millennia of looking up, measuring, counting, always reaching for a number that seems to slip further away the closer we get. And maybe that's the point. Maybe the question was never really about the answer. Maybe it was always about the reaching. Think about what we've learned along the way. Not just numbers, though. The numbers are staggering. From 1,000 to 1 billion to 100 billion to 200 sextillion. But beyond the numbers, we've learned about ourselves, about our persistence, our humility, our stubborn refusal to accept mystery when measurement is possible. Hipparchus didn't need to catalog the stars. His culture had already named the important ones, tracked the planets, marked the seasons. But he did it anyway because knowing mattered more than needing to know. That impulse, that hunger for understanding, echoes through every astronomer we've met along this journey. Galileo could have been content observing Jupiter's moons and collecting his patrons' money, but he pointed his telescope at the Milky Way and shattered the illusion of countability. William Herschel could have stayed a musician, comfortable and respected. Instead, he spent 40 years freezing in observatories, grinding mirrors, sweeping the sky section by section, mapping a galaxy he'd never fully see. Henrietta Leavitt could have resented the low pay and lack of recognition. Instead, she measured variable stars with such precision that she handed humanity a cosmic ruler, even though she'd never lived to see how far it would reach. Each of them made mistakes. Hipparchus thought all stars sat on a celestial sphere. Herschel believed the sun sat at the galaxy's center. Shapley trusted von Manin's faulty rotation measurements. Hubble underestimated distances because he confused two types of Cepheids, but their errors didn't diminish their contributions. They advanced the conversation. They asked better questions. They built tools and methods that others refined and improved. Science isn't about being right. It's about being less wrong over time. It's about accumulating knowledge brick by brick, correcting as you go, trusting that future generations will stand on your shoulders and see farther than you ever could. And we have seen farther. We've mapped the Milky Way in 3 dimensions. We've measured distances to galaxies billions of light years away. We've traced the universe's expansion back to its beginning, 13.8 billion years ago. We've discovered that stars aren't eternal. They're born in clouds of gas, live for millions or billions of years, and die in explosions or slow fades, recycling their material into new generations. We've found that the universe is not just bigger than we thought, but weirder. Dark matter holds galaxies together. Dark energy accelerates the universe's expansion. We don't know what either of them is, but we know they're there. The count has grown beyond stars to include phenomena we can't even see directly. But let's return to the original question. How many stars are there really? The honest answer is, we don't know exactly. The Milky Way contains somewhere between 100 billion and 400 billion stars, depending on how you count and what you include. The observable universe contains roughly 2 trillion galaxies averaging maybe 100 billion stars each, giving a total around 200 sextillion stars. But that's just what we can see. Beyond the cosmic horizon, space continues. If the universe is infinite, the star count is infinite too. If it's finite but vastly larger than the observable portion, the count could be orders of magnitude higher than our estimates. We're counting what we can see and guessing at the rest. Does that bother you? That we've worked so hard for so long and still don't have a definitive answer? Or is there something beautiful in the incompleteness? The universe has given us a task we can't finish. We can count and count and count, improving our methods, building better tools, cataloging billions of stars. But we'll never count them all. There will always be more, fainter stars beyond our detection limit, distant galaxies beyond our horizon, new stars being born in nebulae as old ones die. The count is dynamic, always changing, forever incomplete. And maybe that's a gift. It means there's always more to discover, always another mystery to pursue. The work never ends because the universe never stops being interesting. Let's talk about what counting stars has taught us about our place in existence. Every advancement in astronomy has been a demotion. Earth isn't the center of the solar system. Copernicus and Galileo showed us that. The solar system isn't the center of the Milky Way. Herschel and Shapley corrected that misconception. The Milky Way isn't the only galaxy. Hubble proved Curtis right. And our galaxy isn't special or central among galaxies. It's just one of trillions, sitting in an unremarkable part of space, orbiting nothing in particular. We've been pushed to the periphery again and again. And yet, somehow this isn't depressing. It's liberating. You're sitting on a planet orbiting a middle-aged yellow star, 2/3 of the way out. in a spiral arm of a galaxy that's one among trillions. Your sun is one of hundreds of billions of stars in the Milky Way. Most of those stars are smaller and dimmer than the sun. Some are larger and brighter. Many have planets. Some of those planets might harbor life. You are made of atoms forged in the cores of ancient stars that exploded billions of years ago, scattering their enriched material into space, where it eventually coalesced into new stars, new planets, and eventually you. You are literally star stuff. Carbon, oxygen, nitrogen, iron, every element heavier than helium in your body was created in stellar furnaces or supernova explosions. You're not separate from the stars, you're part of them. A way for the universe to know itself. Carl Sagan said that once. We are a way for the cosmos to know itself. It's not just poetic, it's literally true. The universe is vast and mostly empty. Most of it will never be observed by anything conscious. Photons will travel for billions of years through darkness, never encountering an eye or a detector. Stars will burn and die unwitnessed. But here on this small planet, consciousness emerged. Beings capable of wonder. Creatures who look up and ask questions. Who build telescopes and satellites. Who spend lifetimes cataloging stars not for survival or profit, but because knowing matters. The universe is counting itself through us. Every star we catalog, every galaxy we map, every measurement we make, that's the cosmos, examining its own structure. And we're privileged to be the instruments through which that examination happens. Think about Hipparchus again. He died around 120 BCE, his catalog preserved by Ptolemy and copied through the centuries. He never knew his work would still be referenced 2,000 years later. He never imagined telescopes or satellites or computers, but his impulse, the desire to measure and understand, connects directly to Gaia's mission today. The same question, the same drive, just better tools. If Hipparchus could see Gaia's catalog, what would he think? Would he be amazed that we've counted 1.8 billion stars? Or would he ask, yes, but how many more are there? Probably the latter. Because the number was never the point. The pursuit was the point. Henrietta Leavitt died in 1921, never knowing she'd nearly won a Nobel Prize. Never knowing her period luminosity relationship would become the foundation of cosmology. Never seeing the Hubble Space Telescope or Gaia or the James Webb, but her work endures. Every time an astronomer measures a Cepheid to determine distance, they're using her method. She's still contributing decades after her death. That's the power of good science. It outlasts the individual. It becomes part of the edifice of knowledge, supporting everything built on top of it. And Hubble. He saw the universe expand. He pushed galaxies from thousands to millions of light years away. But he never knew about dark energy, the mysterious force accelerating that expansion. He never knew the universe's age would be refined to 13.8 billion years. He never saw the cosmic microwave background radiation, the afterglow of the Big Bang. He started a conversation that's still ongoing. Cosmology didn't end with Hubble's law. It began there. So, what happens next? Where does star counting go from here? We're building bigger telescopes. The James Webb Space Telescope, launched in 2021, can see farther into space and time than any previous instrument. It's finding galaxies that formed just a few 100 million years after the Big Bang, when the universe was young and the first stars were igniting. Ground-based telescopes are getting larger too. The extremely large telescope in Chile will have a mirror 39 meters across when it's completed. These instruments will see fainter stars, more distant galaxies, greater detail. The count will keep rising, but there's a limit. Not a technological limit, but a fundamental one. We can't see beyond the cosmic horizon. Light from regions farther than about 46 billion light years away hasn't had time to reach us since the Big Bang. That's the edge of the observable universe. Beyond it, space might continue forever, or it might curve back on itself, or it might branch into parallel universes. We don't know. We can't know with current physics. So The count will always be incomplete. We'll catalog what we can see and acknowledge that the true total is unknowable. And maybe we'll make peace with that. Maybe we'll accept that some questions don't have final answers. They just have better and better approximations. There's a Zen quality to that, isn't there? You set out to count the stars. You spend your life counting. You catalog millions, billions. And at the end, you realize the count will never be complete. But the work wasn't wasted. Every star you counted is a data point, a truth, a small piece of the vast puzzle. And the aggregate of all those pieces across all those lifetimes adds up to understanding. Not complete understanding, not final understanding, but understanding nonetheless. A growing, evolving comprehension of the universe's structure, its history, its nature. That's what 3,000 years of star counting has given us. Not a number, a story. The story goes like this. The universe began in a hot, dense state 13.8 billion years ago. It expanded and cooled. Hydrogen and helium formed. Gravity pulled these elements into clumps. The first stars ignited. They lived fused heavier elements and died. Their death scattered those elements into space. New generations of stars formed from the enriched material. Planets coalesced around some of them. On at least one planet, life emerged. Eventually, that life became conscious. It looked up. It wondered. It counted. And through that counting, it came to understand the very process that created it. That's the story. We're a chapter in it. Maybe a small chapter, maybe a fleeting one, but we're here and we're telling the story, and that matters. Before we drift into sleep, let me leave you with one more thought. Somewhere out there orbiting some distant star we've cataloged but never truly seen, there might be another world. Another being looking up at their own night sky, counting their own stars, feeling their own smallness and wonder. They might be asking the same questions. How many? How far are we alone? They might have their own Hipparchus, their own Henrietta, their own Hubble. Or maybe they've moved beyond counting. Maybe they've answered questions we haven't thought to ask. Or maybe they're long gone, their civilization extinct, their telescopes silent, their data lost to time. We don't know. We might never know. But the universe is so vast and the stars so numerous that it seems almost certain we're not the only ones looking up. And if we're not alone, then somewhere perhaps another consciousness is also marveling at the uncountable beauty above, also feeling small, also feeling connected to something infinite and ancient, also counting stars and knowing deep down that the count will never end. So rest now. Let these thoughts settle softly. You've traveled 3,000 years in a few hours, from ancient Greece to modern space telescopes, from 1,000 stars to 200 sextillion, from a universe that fit inside the Milky Way to one that extends beyond imagination. You've met the counters, the patient, stubborn, brilliant humans who dedicated their lives to measuring the immeasurable, and you've glimpsed the answer to the oldest astronomical question. How many stars more than we can count? More than we'll ever count. An endless, beautiful, overwhelming multitude that reminds us every clear night how small we are and how vast the cosmos is. Sleep well. Dream gently among the stars. Let your mind drift through the Milky Way, past Andromeda, out into the dark spaces between galaxies where light takes billions of years to travel. Know that you are part of this, made of stardust. A way for the universe to know itself. And when you wake, the stars will still be there, waiting, shining, uncounted and uncountable. An infinite gift from a universe that keeps growing, keeps surprising, keeps inviting us to look up and wonder. Thank you for drifting with me through this cosmic journey, for listening to these stories of stars and the humans who counted them. If you found peace in these quiet hours of science told softly, I hope you'll join me again. There are more stories waiting, more mysteries to explore, more wonders to whisper about in the darkness. Until then, rest well. And remember, somewhere above you, right now a satellite is counting stars, adding to the catalog, Continuing the work, Hipparchus started on a rocky island 2,000 years ago. The count goes on. The wonder never ends. Good night,